Hello everyone, my name is Dipayan Jana from Construction Materials Consultants. In this video, I'm going to give some demonstration of thin sections of concrete, mortar, stone, pavers viewed through Basler Microscopy Software. This is the part 2 of the 2 series to show the usefulness of Basler's microscopy camera and the microscopy software in concrete petrography. I'm using a Basler Pulse series microscopy camera. These are the small blue cylindrical cameras. These are Pulse series rolling shutter, 5 megapixel resolution with 14 frames per second frame rate. We don't need a very high frame rate camera for still photos when we don't do scanning of the thin section. When we do scanning of thin section, we use about 60 frames per second Basler cameras. Those are industrial cameras. I'm going to show the microscopy software with the microscopy camera now. So this is the software, Basler microscopy software. When you open that software, I want to first give a layout of different modules in the software. Here you can see the camera control module on your left, and you can go between the adjust display and the camera control module. And in the camera control module you have exposures, either automatic or manual. I highly recommend to use the manual exposure, where you control the exposure time of your samples and keep the gain value minimum to get a sharper image, and play with the exposure time at plain polarized light and the cross polarized light mode. Usually I don't play with the hue or saturation or brightness, contrast, sharpness values unless I feel them to change a little bit. The 14 frames per second frame rate, we can use the live mode at the highest resolution of 2592 by 1944, and the capture resolution is same. Usually in most cameras the live resolution we keep low for good frame rate, but in this camera we can keep the live and the capture resolution at the highest megapixel, at the 5 megapixel resolution, without seeing any image blur when we move the slides. And you have different presets, fluorescent presets. We can set the preset when we do the fluorescent thin section, but when we do the regular blue dye mixed epoxy impregnated thin sections, we don't need to worry about fluorescent preset. Or when we do the plain polarized light or cross polarized light mode of fluorescent dye mixed epoxy impregnated thin section, we don't need the fluorescent preset unless we go to the fluorescent mode by using a barrier filter and excitation filter combinations. I'm using an Olympus BX series polarized light microscope with reflected light and transmitted light and fluorescent light facilities. I'll be using in this series mostly the transmitted light facility at the plain and crossed polarized light. First thing you have to do is calibrate your camera with a stage micrometer. And when we do the calibration, we go to Acquire. You have File, it's a new image, open image, image close, image saving, all the options. Then edit, undo, redo, repeat, cut, copy, paste, paste as, delete, select all, deselect options. In the view you have toolbar. You can play with the toolbar, how many toolbars you want. When we want camera control, we can open the camera control on the top as opposed to on the right side. When we want devices, you can open the devices. So we can open different toolbars Measurement, we can open the measurement toolbar. View. So this is how you can open all the toolbars. Crosshair. So if I go from left to right, you have new image, open file, save file, send email, print directly, print preview, cut, paste, copy, undo, redo, context, help, pan tool, zoom tool, magnifying tool. They will be highlighted when you open an image. Selection tool, marquee tool, move tool, crop tool, confirm input, cancel input, zoom in and zoom out option, then actual pixel, fit to window for the image. Then you have different objective magnifications. So do calibration at different objective magnification. To change from one object to other, you just switch from 4x to 10x to 20x. Once you do the calibration, it will automatically adjust the scale bar based on your chosen objective magnification. This is the adapter magnification. We keep at 1x if we use a 1x. I'm using a Olympus C-mount camera adapter. This is to put the calibration. This is the device setting. When we play with the device, different brightness, contrast, device setting. Live mode, and this is the capture mode. This is the exposure time. We choose the manual exposure time. This is the acquisition setting. Load camera setting. You can save every camera setting you play with as a preset, and you can open that. So you don't have to play with the brightness, contrast, hue, saturation, exposure time, gain, all these parameters every time. If you don't change the lighting condition or your sample, then you can set a preset value for each and save the preset and open that preset for the camera setting. Toolbar, tool window, scale bar, info stamp, crosshair. If you want to give a crosshair on your sample, usually when we do the air void analysis, we need the crosshair. Maximize to screen, select measurement object, arbitrary line, 3-point angle, closed polygon, select measurement. So these are different tool options present. So best thing to do is first let me show you how we do the calibration. We put a micrometer first, stage micrometer. We go to live mode. Go to plain polarized light. And then we bring a micrometer in the middle. Reduce the exposure time to see the micrometer. Focus it. Smallest division is 0.01 millimeter in this micrometer. So first thing we do is we go to calibration, either here, aqua calibration, or we can do the calibration right here. And once we do calibration, we give the camera, it's a USB 3 camera that we are using, and then we say calibrate. Once we calibrate, we have to give the objective magnification and the zoom magnification, the adapter magnification. If there is a variable magnification for the C-mount adapter as opposed to fixed, you have to choose which magnification we want. Since I have done the magnification before, I just want to show you how to do it. Suppose you have a 4x, then all you do is remove everything else, all other magnifications. And if your C-mount adapter magnification is 1x, you stay at 1x, you remove all other options. Then you go to next. Then you put a known distance for a 4x objective and 1x C-mount adapter. You draw a line, and to draw a line you just set reference distance. Then you draw, this is 1 millimeter from one end to other. And then you press the enter button, and then you see this is 1 millimeter, or you can say 1000 micrometer. Okay, that's how you set the magnification. I don't want to set the magnification since I have done it. Since I have done it, so I want to cancel it. But that's how you set the magnification for 4x. And once you do 4x, you change your objective to 10x, 20x, and that's how you set the magnification. And then it gives a scale bar based on your magnification. You can turn on and off the scale bar. You can see 200 micron is 0.2 millimeter. You can bring, after you do the magnification, after you do the calibration, you bring your scale bar, you bring your objective to see the length. You can see it's 0.2 millimeter, 200 micron. You check your calibration after you finish with the scale bar and the micrometer, stage micrometer, that you are correctly getting the scale bar for that objective magnification. We're using 4x now. So this is how you do the calibration for different objectives using the stage micrometer for a fixed C-mount adapter. If your C-mount adapter has a variable magnification, then you need to make sure that you calibrate at different magnification of your C-mount adapter. That's why this software is, Basler Microscopy Software gives you options for all permutation combination of objective magnification as well as adapter magnification. And if you don't change the adapter, if you keep it at 1x for example, then all you need is just the calibration for different objective magnification. So that's how you do the calibration part first, so that you can put a scale bar in your image. And as I said, it's good to keep in the manual mode, so we can play with the exposure time to change the image from brighter to darker. One thing you have to do is to make sure that the white balance is adjusted. So this is the auto white balance, this is the focus indicator, this is the grayscale mode, RGB grayscale mode, acquisition setting, adjust display. You can play with those options once you get an image. But usually I don't change I just make sure that I get the right white balance. We keep the auto white balance on, and I just play with the exposure time when I put an image. Okay, so first sample I'm going to place is not a concrete sample but a stone paver. This is a flagstone paver, a slate flagstone paver with cement sand jointing mortar. So this is a large area thin section of 50 millimeter by 75 millimeter size, 2 inch by 3 inch size thin section, where I have a portion of the slate paver from both sides and a central jointing mortar. I'll show you. And the sample is impregnated with a blue fluorescent dye. Let's see the sample in plain polarized light. focus. Here you can see the slate, the low-grade metamorphic rock, where mudstone shell, the sedimentary rocks transform to slate, showing the typical slaty cleavage, which gives the rock the tendency to break into flat pieces. That's why it's called flagstone, commonly used in roof or paver for its tendency to break down into flat pieces from the slaty cleavage. There are many sandstone with fine bedding planes also are called flagstone. These are either very fine grained sandstone with layers or slate with slaty cleavage, shows you this tendency to break the rock into flat pieces. That's why these are known as flagstone. And here is a slate sample. You can see the fine lamellae of fine bands of argillaceous material, clay and silt, and interbedded with some calcareous, calcite, fine-grained calcite-based material. You can see a crack here, which shows in blue dye. The problem in this particular paver is splitting or scaling of the slate paver, especially adjacent to the mortar, adjacent to the jointing mortar. Here you can see a portion of the slate been flaked off right adjacent to a jointing mortar, which is right here. You see how the light come back by auto white balance adjustment. The light was bright red and then slowly it came back to the natural color. And this is a jointing mortar. This is Portland cement and silica sand based mortar. This is 1 part cement to 2 part sand, no lime, just a cement only. Binder 1:2 ratio. Usually in paver, the jointing mortars are either 1:1 or 1:3 ratios of cement to sand. Also, hydrated lime is used in many mortars to improve the workability and water retention properties. But in this particular jointing mortar, 1 part Portland cement and 2 part silica sand was used. This is a jointing mortar in plain polarized light. You can see well hydration of cement. There's very little residual cement particle. Also, there are patches of areas in the paste which are darker, denser, due to inadequate mixing of cement and water. You will have dark patches and porous areas, dark areas, which shows the mixing of cement and sand wasn't uniform to create a uniform homogeneous porosity of paste. You have some areas porous, some areas dense, and the denser areas you have a lot of residual cement particles. You can see the residual cement particles left in the dense patches, whereas when we go to the porous patches of paste, you don't see the residual cement particle except some dark skeleton of the ferrite phase. And here the paste is porous, so it absorbs the blue dye, blue epoxy, so it shows much darker blue color, as opposed to less blue color in the darker, denser areas due to lesser absorption of the blue dye. This is a secondary calcite precipitate, secondary calcium carbonate, created efflorescence deposit on the stone, and usually these efflorescence deposits are found in the field at the interface between the mortar and the stone, where the ingredients of the efflorescence came from the dissolution of the cement hydration product of the masonry mortar, of the mortar joint. And that dissolution by moisture entered through the interface between the mortar and the stone, caused dissolution of cement hydration product, mostly the calcium hydroxide component of the cement hydration product, then that dissolved lime, dissolved calcium hydroxide came out to the outside to the air, and then water evaporated, and then it precipitated the dissolved constituents, which eventually carbonated in the atmospheric carbon dioxide in contact with carbon dioxide and formed calcium carbonate. So that's how the efflorescence deposits are formed, preferentially at the interface between the stone and the mortar. Here comes the stone again. You can see a crack, an incipient crack highlighted by the blue epoxy right at the exposed surface of the paver. This paver is about 3/4 inch, about 19 to 20 millimeter thick, and at the top around 0.1 millimeter, about 100 micron, 50 to 100 micron thickness of the paver has been scaled off or created the near surface cracks, micro cracks. And this is the entire section of the paver which has been scaled off from the main body. So that's the scale, that's the delamination plane, you may say, where this portion, which is about 0.2, 0.4, about a millimeter thickness. If this is 0.2, about 0.1, 2, 3, 4, 5, about 1 to 1.2 millimeter thickness portion of the slat has been scaled off, flaked off from the main body. And that happened from using a rich cement mix in the mortar with no lime, where a mortar created undue stress on the slat, and the slat, having the slatty cleavage, created the scaling on the surface. You can see the silt and clay mixture. In some areas you have fine-grained darker brown layers of carbonaceous and argillaceous materials in the slat, and some lighter areas where you have more of calcite, carbonate areas. These are calcite rich areas. These are carbonaceous, argillaceous areas. Some secondary calcite precipitate in the void spaces. So this is the scale, this is the slat paver. Now I'm going to show the crossed polarized light now to show how the slat thin section looks in crossed polarized light. So if I insert the analyzer, I need to increase the exposure time a little bit. So you can now see the thin section of slat paver. The fine-grained carbonates coming as layers, alternating with argillaceous layers. So you have alternate arrangements of calcareous and argillaceous layers in the slat. And you can see silt size quartz grains, some of the silt size quartz grain. Clay is difficult to see in the 4x magnification or in a petrographic microscope. You won't be able to see the clay clearly, except some very fine flecks of mica, sericite, kaolinite, halite, some flecks you will see at high magnification. These are silt size quartz grains. Here is a mixture of calcite and quartz in these carbonate areas. You have carbonate patches, calcite and quartz, and these areas are quartz and clay. Again, there is a carbonate band. So you have alternate precipitation of argillaceous and calcareous materials in the parent rock, which is the shell, which has been metamorphosed to slat by low-grade thermal metamorphism or regional metamorphism. You form this slat. There is a more or less homogeneous mixture of very fine-grained clay and silt. You have the dark brown bands which you saw in the plane polar. If I increase the magnification from 4x to, let's go to 10x. or maybe 20x, you can see the fine-grained silt and clay matrix even better. And since I changed magnification from 4 to 20, I go to 20x here from 4 to 20. Look, the scale will change. The scale become, this is the 20 micron. So every time you change the magnification, you select the objective that you have calibrated before. So the scale bar will be adjusted based on your objective magnification. Here you can see the fine-grained clay with platy cleavage and the sill size quartz. Mixture of muscovite, biotite and different clay minerals, kaolinite, elite, and also mixed with some fine-grained calcite. Once in a while you will see calcite in the dominantly argillaceous matrix. You can see the clay minerals here. Mostly the sill size quartz grains are less than 20 micron in size. There is a calcite grain. So let's go back to 10x. It will adjust the when you choose the auto white balance, it will adjust the white balance to give you the accurate representation of what you see through the eyepiece. Let's go to the jointing mortar. There is the mortar. This is the interface. You can see the carbonation at the interface between the slate and the mortar joint. This is the carbonated portion of the joint where the paste has been carbonated. You see some residual cement particles still present in the Portland cement paste, which has been severely carbonated along the interface. And here is the fluorescence deposit, layer by layer precipitation of secondary calcite. This is the quartz grain calcite precipitate, where the calcite came both from the cement hydration product, and part of the calcite also came from the calcite in the slate matrix. At cold condition, cold weather, when you have cold water entered into slate, that will dissolve calcite more efficiently than water. Then warmer water, calcite has a reverse solubility. So at cold condition, calcite will dissolve readily in a cold water. So if the cold condition, this calcite, part of the secondary calcite can come from the calcite in the slate, but mostly the calcite, the secondary calcite, came from the carbonation, from the cement hydration product in the mortar. Here you see the carbonated portion of the mortar, and this is the interior non-carbonated portion. This is the surface region of the mortar at the very top. This is the very top of the jointing mortar. You can see the carbonation of the paste with very little cement particles. There are some patches of quartz grain secondary calcite formed from dissolution and reprecipitation of fine grain calcite from the carbonated portion. Then this is the non-carbonated interior part of the mortar, where you have Portland cement paste and the sand particles. Here you see some calcium hydroxide crystals, some platy and patchy calcium hydroxide crystals, which are the product of hydration of Portland cement. The primary calcium hydroxide crystals, and most of this calcium hydroxide crystals has been dissolved by the migrating moisture to create the efflorescence. So the top portion of the mortar, you see very porous paste, and this porous paste is the result of leaching of the calcium hydroxide from the paste, leaching of this lime of the calcium hydroxide. So this skeleton, what you see here, is a non-carbonated but porous leached skeleton of the paste, where the lime portion and the calcium silicate hydrate of cement hydration product and the calcium hydroxide component of cement hydration product has been leached out partially, because you still have some calcium hydroxide crystals left. Partially it has been leached out by the migrating moisture and formed calcium carbonate, either carbonated paste or the calcium carbonate efflorescence at the surface. The ingredient of the efflorescence deposits came essentially from calcium hydroxide component of cement hydration and calcium silicate hydrate. So as I go deeper and deeper into the paste, into the mortar, paste fraction of the mortar, you see more and more calcium hydroxide, which is the more pristine interior portion of the mortar. You see a lot more calcium hydroxide which has not been leached out. Which has not been leached out. But you have a lot of leaching happened in this jointing mortar due to moisture migration. And you can see all these porous areas, all the porous patches in the plain polarized light where lime has been leached out by the migrating moisture. But if I see this is a 10x magnification, if I see the denser area, you still see some residual cement particle. Here you can see a residual alite with the dark brown ferrite phase of the Portland cement. But for most cases, the cement particles have been well hydrated, so you don't see so much residual cement particles. Here you can see a lot of leaching or dissolution happen. A part of the reason the paste is so porous is not just because of inadequate mixing of water and cement, where the high water cement ratio areas, the patches, are preferentially blue compared to low water cement ratio, denser, darker areas. But also the porous areas, the lime has been leached out by the moisture, which further increase the porosity of those porous areas from leaching of some lime. Here you can see some cases hydration rim around residual cement particles. So the inherent capillary porosity of the paste from the hydration has increased due to further leaching. But as you go deeper and deeper into the mortar, into the jointing mortar, you see lesser and lesser evidence of leaching and more denser paste with intermittent patches of lighter paste due to local high water cement ratio. You can see the hydration rim around residual cement particles. This mortar is just two-component mixture of Portland cement and silica sand at 1% cement to 2% by volume. Here you can see a lot of residual cement and a really dense area of the paste. And this portion, the paste is densest at the bottom. You see how much residual cement particles, which is a very dense area of the paste at the bottom end of the jointing mortar, where you suddenly see abundant residual cement particles. Alite, belite sphere with interstitial dark brown ferrite, alite and ferrite, dark brown ferrite. You see a lot of residual cement particles and a very dense low water cement ratio paste, where the blue dye didn't absorb to create blue color as the porous areas does. So this area at the very end of the jointing mortar, the hydration, the degree of hydration is much lower than the majority of the mortar. You see a lot of residual cement particles in the paste. Belite, alite with ferrite, belite with interstitial ferrite, all the residual cement particles and the very dense paste you can see at the bottom. If I go down to 4x magnification, Let the color adjust. You go to 4x, back to 200 micron scale bar to show the denser areas at the bottom. You see how dense the paste here is at the bottom end. And then you have some secondary calcite from the moisture migration at the base of the paver, at the base of the mortar joint. You still have secondary migration. This portion you see a lot of secondary calcite, secondary calcium carbonate from moisture migration. So this is, and here you can see the stark difference between the dense and porous areas of the paste in the jointing mortar. With the cross polar, you can see moisture migration in the porous area and also migration of carbon dioxide to carbonate the paste in the porous area. And the dense paste also got carbonated because atmospheric CO2 came down through the interface between the mortar and the slate paver to eventually carbonate even the denser areas of the paste. So there was a ready access of not only moisture but CO2 to cause the carbonation. Here you can see the secondary calcium carbonate ring formed at the edge of the dense paste of the jointing mortar. This area is very dark because of the leaching, but the calcium hydroxide component and the calcium silicate hydrate component of the cement hydration has been leached out. So it created a more or less porous patches of the paste. Left is the, you can see the overall blue color of the paste as opposed to dark brown color in the denser areas. In this portion, leaching has occurred, and the cross polar, you don't see, when you go to cross polar, you don't see so much lime, so much calcium hydroxide because of leaching, except the residual remains that left. That's the boundary between the mortar and the slate. So this is the first thin section I showed with the Basler microscopy camera, how this camera can be used at high magnification. Here is the crossbar you can place. And this is only 60% view. If you make it 100%, so you get a much bigger area. And this is a 32-inch monitor, so you can really see the microstructure in greater detail when you use a larger monitor. And you can see a very good frame rate, even 14 frames per second. When I move the slide, you don't see so much image blur. Even at the highest magnification of 5 megapixel in the live mode, you have very little image blur. So this is very good camera at 5 megapixel, 14 frames per second frame rate. You can play with the movement of the slide with very little image blur. So this is the first thin section I showed. Now I'm going to show you one from a concrete sample. The second thin section I'm going to show is of a concrete from a high-rise building in an oceanfront environment in Puerto Rico. This concrete showed corrosion of steel and spalling in the balcony slabs. So we got a sample, a core drilled from the balcony slab from an area where this corrosion related spalling has occurred. They want to see the condition of the concrete and if it can be serviceable. We have multiple layers of protective membrane applied on this concrete to prevent migration of chloride moisture from the air. This is a building in an oceanfront environment with a high chloride and moisture in the air to cause corrosion of steel. So a number of protective layers will be found in the thin section of the concrete. When you have this kind of scenario, a careful preparation of thin section is important, and documentation of all the layers present, the density, the porosity, permeability of the layers, the compositions of the layers, and if the layers are effective in preventing migration of moisture chloride from the air to the concrete. So here is the thin section. I go to the live mode again. And let's start from the top, on the edge of the thin section. Here you can see in this particular area of the building, they have multiple paint layers at the surface, where you see an acrylic paint layer at the top with an acrylic binder and talc and fine clay as a mineral filler. Talc is a very common filler used in many paint. Here you can see a top layer of the paint, and this is the 4x magnification. This is the 200 micron size, so it's about 200 to 300 micron thickness, 0.2 to 0.3 millimeter thickness paint layer at the very top with some fine-grained mineral filler. And when you go to the cross polarized light, you see the carbonated concrete in this portion, but this is actually a cementitious coating, cementitious coat of the protective membrane. I'll come to that point later. Let's concentrate on the paint layer, and if I increase the exposure time to bring the paint layer visible in the cross polarized light, you can see different composition of the acrylic binder, which has created different interference color in the cross polarized light. You get a reddish brown color paint layer and a medium brown color paint layer and a porous kind of blue color paint layer at the top. And this paint layer, they're all acrylic binder, they're all acrylic medium, but this top layer, about 0.2 to 0.3 millimeter in thickness, has some fine sill-size quartz and some talc as mineral filler, and there are also some dark color opaque fillers present. Some of these opaque grains are pigment they added to the paint for the coloration. Some of these are titanium oxide pigment, and is a mixture of titanium oxide, very fine silica, and mineral filler of talc and clay based mineral filler, and the overall acrylic binder. This paint layer was applied on top of another one or two different paint layers. You can see there are multiple applications of paint layer at the surface. Let's go back to the plain polarized light view. Reduce the exposure. You have to play with the exposure time every time you go from cross to plain polarized light. It's still preferred than using in the automatic mode. Here you can see there is a thin cementitious layer came in the middle between the top acrylic layer and then the intermediate acrylic layer, then the bottom acrylic layer. So you have multiple applications of acrylic layers, a paint layer with interstitial layers of cementitious materials, which has been, if you go back again, which there it is, let's reduce the exposure, which has been carbonated. This is the cementitious layer in between the paint layer, which has been carbonated. We go back to the plain polarized light mode, and then after this paint layer, let's go from top to bottom to show all the layers. Very top you have this acrylic layer with filler, then you have neat acrylic layer, I can say 1A, 1B, 1C, three different layers. Then number two is the cementitious coating. It's a cementitious mortar coating they apply it on the concrete surface. You can see it's a very dense paste with a lot of residual cement particles. You can see the B-light with ferrite interstitial, spherical B-light clusters with interstitial ferrite, the allied grains. So all the residual cement particles and the cement hydration products are present. And this mortar has silica sand and seashell. It's a mixture of silica sand and seashell. Being in Puerto Rico, seashell is a common ingredient used in the sand. Here you can see a B-light cluster in the middle with interstitial ferrite phase of the residual cement. There are abundant residual cement particles scattered throughout the dense Portland cement paste. So this is the denser part of the mortar, protective mortar coating. Then you have a relatively porous part of the mortar coating. And this denser part of the reason the paste is densified is because it's been carbonated. And I can show you by going to the cross polarized light mode. The denser part you can see is carbonated, whereas the relatively porous part in the middle, relatively less. Adjust the brightness, exposure time. I'm not really playing with the brightness, I'm just playing with the exposure time. You can see it's more carbonated and relatively less carbonated, and you go down more, you see carbonation of paste, but it's the porous area, then relatively less carbonated portion coming in the interior of this mortar coating. This is a thick, about 20 millimeter thickness mortar coating, where you have mixture of silica sand and seashells. You can see spectacular microstructure of the seashells, coarse grained calcite, the residual cement particles, feldspar. There is a small granite sample with secondary calcite rim around the granite, seashell. There is a pathetic feldspar. And being in Puerto Rico, in an island arc volcanism setting, you have volcanic rocks as the main ingredient of aggregates used in this concrete and also in this mortar coating. You will see a lot of volcanic rocks, andesite, dacite, trachyte, rhyolite. These volcanic rocks are present in the aggregates, in the fine aggregate and coarse aggregate. But in the mortar coating on the top, you have a lot of seashells as well as aggregates. Here you can see sericitic alteration of feldspar. This is an albitic feldspar with sericitic alteration. You see seashell. You can see the albite twin of the albite feldspar. 3 feldspar grains with twin lamellae. As I'm going up towards the surface region of this mortar coating, you see more and more carbonation. Then this is kind of the boundary between the dense paste and less dense paste. The dense paste is severely thoroughly carbonated. And this is the exposed surface region of the mortar coating before the paint layers were applied. So paint, then the dense exposed surface region of the mortar coating, then still carbonated but less dense interior portion of the mortar coating, where you have different degrees of carbonation. As you go deeper and deeper, the carbonation goes down and you get more pristine paste of the mortar coating. It's a straight Portland cement based mortar coating with a mixture of Portland cement, silica sand and seashells. After this mortar coating, let's go back to the plain polarized light mode, adjust the exposure time. You can see a lot of residual cement particles and the paste. As you go still down, more or less uniform distribution of residual cement particles in the paste. Seashells with layer by layer seasonal formation, annual formation of the rings, the growth rings on the seashell. Then you come at the very end. This is the interface between the concrete, the main part of the concrete, and the mortar coating. This is the interface between the mortar coating on the top and the concrete on the bottom. And you can see the exposed surface region of the concrete is kind of porous with a lot of interstitial pores and capillary pores at the surface region of the concrete. And the concrete surface region is, you can see the porous areas at the surface highlighted by the blue epoxy. Dense paste, porous paste. All along the top end of the concrete you see this porous layer. About 100 micron, half of this length, or maybe 200 micron in thickness, the porous layer. And if I go to cross polarized light, you see that all this portion is carbonated and leached out. You can see here, if I go to cross polar, that portion, the part of the region of increased porosity is leaching and carbonation of the paste at the surface region of the concrete. This is the concrete part, the mortar on the top, and then the dense portion of the concrete is carbonated. Then after this dense surface region comes the interior. You see a volcanic rock here, dacite and andesite. Now comes the interior, is a rhyolite. Now this is the interior non-carbonated portion of the concrete. And you can see a lot of volcanic rocks. These are all showing the porphyritic texture, typical porphyritic texture of volcanic rocks, with euhedral to subhedral phenocryst of plagioclase feldspar, albite, oligoclase, and andesine-based plagioclase feldspar with lamellar twinning. You have some phenocryst of large coarse grain crystals of feldspar, as well as fine grained laths, crystallites and microlites of feldspar in a dark ferruginous glass matrix. This is a volcanic rock called andesite, where you see this phenocryst of feldspar with lamellar twinning. The twin lamellae, you can see simple twinning of the feldspar of the plagioclase phenocryst in this andesite. Sometimes you get a cluster of phenocrysts, cluster of plagioclase phenocryst, which is called glomeroporphyritic texture, as opposed to simple porphyritic texture of phenocryst of coarse grain crystals in a fine grain groundmass. The typical volcanic rock of Puerto Rico. This is in an island arc setting, in a subduction zone. You get this andesite, dacite, trachyte, rhyolite, volcanic clan. Then comes the non-carbonated portion of the paste. As you go towards the exposed surface region of concrete, you have a quartzite in the fine aggregate, and then this is the boundary between the interior and the carbonated portion of the concrete. And then carbonated portion goes from porous carbonated portion to denser carbonated portion at the very top. And after the denser carbonated portion comes another top layer of porous carbonated leached portion. Then comes the mortar coating. So we have a zoned microstructure from leached porous surface region carbonated, then dense carbonated surface region, then less dense carbonated surface region, then non-carbonated interior concrete. So you have multiple layers of microstructure showing different events happened at the exposed surface region of the concrete before the protective mortar coating and the paint combinations were applied. So there was a period this concrete was exposed to atmospheric moisture and chloride and carbon dioxide, which has caused the spalling of concrete in the balcony slab before they decided to put this protective mortar coating and the paint combination. Now this protective coating is still carbonated and porous. It's not as dense as it should have been for adequate protection. You can see how porous the protective mortar coating for most of the portion is. The water cement ratio here is estimated to be 0.45 to 0.50 in the mortar coating paste, and then majority of the mortar coating, it's about 20 millimeter in thickness. About 15 to 16 of that 20 millimeter thickness is this kind of semi-porous, semi-dense paste, more or less uniform cement hydration, and then comes the denser paste. The entire region of the mortar coating should have been as dense as this portion. The entire part of the mortar coating should have been this kind of dense paste, which is only present at the surface. And in this case, the dense paste is the virtue of the carbonation of the paste. The carbonation has increased the density and decreased the porosity because the calcium carbonate product of carbonation takes larger volume than the calcium hydroxide crystals of cement hydration that it replaces. So a smaller volume calcium hydroxide carbonate to a larger volume calcium carbonate, as a result of the carbonation, paste usually densifies unless the carbonation affects the calcium silicate hydrate component, where the paste gets more and more porous by dissolution of the calcium silicate hydrate, decomposition of the calcium silicate hydrate. But for carbonation of the calcium hydroxide component, paste usually densifies, as you can see here. And this densification is the beneficial aspect of the carbonation here, because it prevents migration of the carbon dioxide beyond this carbonated densified layer. The entire mortar coating should have been that kind of dense, but the interior, the majority of the mortar coating, is rather porous with a lot of cement hydrates and residual cement particles. All these cement particles should have been hydrated to increase the overall porosity of the paste for this coating to be effective to prevent migration of corrosive agents from the air. And as a result of somewhat porous nature of the paste, the blue dye has been absorbed in the paste to give this blue color, as opposed to the denser patches where the blue dye didn't absorb. So after the mortar coating, you have this densified carbonated concrete portion. After the top layer of the porous carbonated concrete, after the densified carbonated concrete comes, you can see it's also only Portland cement as the sole cementitious material, no fly ash or slag or silica fume. Any other pozzolanic or cementitious admixtures are not added, only Portland cement. A mixture of silica sand and the volcanic sand and the volcanic gravel and crushed gravel coarse aggregate. That's the recipe of this concrete. The water cement ratio is estimated to be around 0.45 to 0.50. In that range, you have a lot of residual cement particles. Degree of hydration of cement is good. There is no evidence here of any restricted cement hydration in the paste. I'm traversing through the concrete portion now, from the top of the thin section to the bottom, which is about 3-inch long thin section. So about the top 3 inch of the concrete is examined in this thin section. There is a residual cement particle with the belite clusters and the residual interstitial dark brown ferrite phase. There is a volcanic coarse aggregate with ferruginous glass matrix, which is very common in many rhyolite, dacite volcanic rocks. You get brown ferruginous glass from iron enrichment during magmatic differentiation. Here you see more or less uniform size laths of plagioclase feldspar in a dark brown glass, interstitial glass. These are all plagioclase feldspar. With the opaque magnetite, hematite, opaque minerals. You get some pelagonite, green pelagonite alteration of glass. This is a diabase, micrographo diabase, intermediate basic igneous rock. This doesn't show the typical porphyritic texture of a volcanic rock. It's more equigranular texture of plagioclase laths and glass matrix. Paste with scattered sand grains of the fine aggregate. A lot of iron oxide opaque grains in the volcanic rocks. Here you can see the layers of opaque grains in the aggregate. Most coarse aggregate particles across gravels of dacite, andesite, rhyolite, rhyodacite. So I'm going around the aggregates. You can see more glassy matrix with phenocryst of plagioclase in an andesite. Beautiful plagioclase phenocryst in a fine grain glassy matrix of andesite. Many mafic minerals are present in the fine grain matrix, in quartz, feldspar, mica, mafic minerals, chert. So, piece of granite. So it's a variety of fine aggregate from feldspar, quartz, chert, granite, volcanic rocks, mostly siliceous sands. Basalt. There are very few basalt in this particular sample, but many other rocks, many other concrete samples from Puerto Rico, you see basalt as the ubiquitous aggregate, depending on the aggregate source. You can see a lot of alteration going on in the volcanic rocks. Carbonated paste. Again, I'm at the very top of the concrete. After carbonated paste comes the mortar coating, rather porous layer of the mortar coating. Seashells quartz, feldspar, CCl, three main ingredients of the mortar sand. Carbonated Portland cement paste of the mortar coating. Then comes at the top denser part of the mortar coating, and after denser part of the mortar coating comes the very top sand, a very top acrylic layer. So these are some airborne fibers came on the thin section. Usually I don't put any cover slip on the thin section because after optical microscopy I do scanning electron microscopy, so I don't put any cover slip. I put a thin film of oil, immersion oil, and then I clean the oil, wash the thin section for putting a gold on carbon coating. Usually I use a gold coating to do the SEM observation. Here you can see you get a large area in this camera to be covered. This is at 4x, of course. This is a 4x objective. So you can see the paint layer and the denser portion of the mortar coating in one. Usually I take one, then another overlapping, two, about three, four, like that. Multiple sections I take like that to stitch to get a continuous profile from top to bottom. I take about 10-15 images like that to cover the entire protective coating in one area, and then in another area I take another traverse like that. Usually I take around 2 traverses from top to bottom to cover the entire protective coating system of concrete. We calculate the thickness of the layer, the composition of the layer, the condition of the layer, the interfacial bond between the layers, and the bond between the protective coating and the concrete, the carbonation of the concrete, the depth of carbonation of the concrete, the different layers in the concrete from the porous layer to denser layer, then the type of paste, whether it's a Portland cement only or if there is any fly ash or silica fume, the type of coarse aggregate, the type of fine aggregate, if there is any secondary minerals present in the air voids, if there is any micro cracks or cracks present, any kind of distress, if there is any alkali aggregate reaction happening between the aggregate and the paste. All those features are observed when we look at a thin section of concrete. The degree of cement hydration, the porosity of the paste, if the porosity varies from top to bottom, if there is any dense areas of the paste, porous areas of the paste, how deep the depth of variation of a particular feature. So a large number of information can be obtained when we look at a thin section of concrete in a petrographic microscope. And the Basler microscopy camera is very helpful for a quick observation in a large area of, here you can see the spherulitic glass on a spherulite. This is a rhyolite volcanic rock, but you can see this hair-like spherulitic texture. So this is how we do petrographic examination. Here is a coarse residual cement particle with subhedral alite and interstitial brown ferrite face. So this is like a movie. When you go down from top to bottom, look at the thin section. Usually I look through the eyepiece of the microscope, and if I see something interesting, then I take a capture an image. I basically keep my eye attached to the eyepiece of the microscope, my left hand on the fine focusing knob of the microscope, and the right hand on the mouse to capture image. Anything interesting, then I continue capturing images with this snapshot mode. And usually I'll show you when you capture those images, don't save any. If I remove all the images, see how easy it is. I'm in the live mode. If I want to capture this, I just go to snapshot and immediately capture one image. Then I go to cross polar at the same position, increase the exposure time, another snapshot, then I got the second image. Then I go back to the plane polar, adjust my exposure time, go to a different area. So I'm at the interface between concrete and mortar, and there I make sure the focus is good. I go from both end of the out of focus to focus. Then I take a snapshot. That's how you get the image. You always have the live image. Then you go to cross polar, increase the exposure time, another snapshot. So that's how you build up your image library when you look a thin section. And after that, you can go back to the image. It's already saving the scale bar from the live mode, and then you can then go to right click, save, and then you can save it. Or you can go to save as, and you decide if you have if you decide like I'm saving in this particular folder, but you can predetermine which folder you want to save. It's going to save automatically as you are capturing. It's going to save automatically in your predetermined folder. So you concentrate on looking in the microstructure rather than whether it's been saved, and you just click the snapshot button. Every time you click the snapshot button, it builds up the image library. Okay, so this is the thin section of the concrete from an oceanfront environment in Puerto Rico, where you had multiple layers of paint and cementitious mortar coating applied on top of the concrete. Overall condition of the concrete in this particular thin section is good, with no evidence of any chemical or physical deterioration. The protective coating could have been better, densified, more densified, then it would have been less carbonated. The fact of the matter that the protective coating is carbonated is a testament of its inherent porous nature. The entire depth of the mortar coating, you can see the paste has been carbonated. You have patchy carbonation in the interior to severe carbonation at the exposed surface region. So to minimize the carbonation of this mortar coating would be the goal for it to be effective to prevent the concrete from penetration of corrosive agents. The fact this mortar coating is carbonated so much in the interior indicates the coating could have been densified with a better degree of cement hydration. You can see a lot of residual cement particles still present in the mortar coating. You can see a lot of cement particles present, which could have been hydrated to densify the paste of the mortar coating. That would have reduced the degree of carbonation of the mortar coating and more effective for prevention of migration of corrosive agents. Okay, so this is the second thin section I showed with the Basler camera. The third thin section that I'm going to show you is thin section of a refractory mortar and brick from a chimney environment, where they used a liner, a refractory mortar liner on the chimney wall of a brick masonry wall, and I'm showing the thin section of the brick portion of the sample, where you can see the sample was impregnated with the blue dye mixed epoxy, which highlight all the elongated parallel voids. These voids are very typical of any brick. Most of the bricks where you have firing of clay, the water released from the firing of clay, the excess water, then the shrinkage causes these elongated voids with tapered ends. And these are very typical characteristic feature of many clay fired units. These are described as elongated voids or parallel lineation or shrinkage microcracks. These are thermal shrinkage of clay. These are very typical, all these elongated voids shown by the blue dye. And when we describe the microstructure of brick, we usually describe as two essential components: the plastic component and the non-plastic component. The plastic component comprises the fired clay matrix, which shows the typical reddish brown color of aluminosilicate glass. Mostly the fired clay matrix is aluminosilicate glass with different degrees of firing of the original clay matrix. That's the plastic component. And then the non-plastic component. The non-plastic components are tempered additives, which are added for the improved performance of the brick, as well as the original component of the clay. And in the tempered additive, you have rock fragments, mineral fragments, mostly quartz sand. Here you can see a lot of quartz sand, as well as previously fired bricks, which are called grog particles, G-R-O-G, grog particles, previously fired brick fragments, organic materials, organic matter you see many times. And when you see the non-plastic component, we determine how many populations of tempered additives are there. Like when the sand is added, you see two, like in this particular case, you see one grain size of sand, one population of tempered sand additive, and then the other population is the cores of particles, which comprise mostly the grog particles. These are the grog particles of previously fired brick. There is another grog particle. So this is a typical brick microstructure with parallel voids, elongated voids from the loss of water during firing from the clay matrix. And then comes on the top, the inner wall of the chimney, you have refractory motor. And this is the interface between the brick and the refractory motor. The refractory motor is a calcium aluminate based motor, which is a very typical motor used in chimney environment or any high temperature refractory environment where the calcium aluminate cement is used. And you have a quartz sand and calcium aluminate cement based motor here. And this motor has a mineral called pleochroite. And these pleochroite minerals, these are the pleochroite minerals. Here is one. These are all pleochroite minerals. These are typical skeletal microstructure of, these are mostly calcium ferrite phase, dark brown color, with a very typical microstructure. If I go to 10x magnification, these pleochroite minerals are very clear here. This is a typical microstructure of calcium aluminate cement mortar, refractory mortar. You can see this pleochroite. And silica sand. This is not a Portland cement mortar, but a calcium aluminate cement mortar. But this mortar has abundant ferrite phase, calcium ferrite phase, the pleochroite. And the silica sand. This is the typical mortar you see. If I go back to 4x again, typical mortar you see in a chimney environment. We have quartz sand. If I go to cross polar, you see two population of quartz sand, a coarser fraction and a finer fraction, and a reddish brown matrix of the calcium aluminate cement paste. This is the exposed surface, the chimney is exposed wall, but you have a lot of carbonation. There is a strained quartzite grain in the refractory mortar, mostly consisting of quartz sand, single crystal, polycrystalline quartzite. Many of these cross grains are strained with undue loose extension. This is the carbonated portion of this top portion is about 200 to 300 micron thickness, 0.2 to 0.3 millimeter carbonated portion at 4x magnification, where the chimney's inner wall of the calcium aluminate cement mortar, where you see the carbonation. Then inside you have the non-carbonated reddish brown color paste in the cross polarized light. If I go back to plain polar again, reduce the exposure time, you can see it's a non-air entrant calcium aluminate cement mortar. And then comes the brick, and in between the brick there is another type of mortar which is also common in many chimney environment. Here you have crushed silica. You see two population of sand, a coarser population and dominantly finer population. The finer population is finely crushed silica sand, and also it has silica flour mixed as a cementitious material with polymer. There's a mixture of polymer, silica flour in a crushed silica based mortar. It's not a typical masonry mortar, but this kind of mortars are common in chimney environment. This is similar to fretwork you see in ceramics, where you use crushed silica, a lot of crushed silica, and you can see that mortar used as a jointing mortar between brick. There is a coarser fraction of silica sand and finer fraction of silica sand, a finer fraction of crushed silica. And if I go to cross polar, all you see is crushed silica sand. And the paste is made using silica flour and polymer. There is no Portland cement or no calcium aluminate cement. This is another type of refractory mortar, jointing mortar used in the chimney environment. A lot of crushed silica. If I go to the other side, following this joint, this is a large area thin section, so I have a lot of area covered in the thin section. And then comes the major part of the mortar. You see this salt and pepper appearance in the paste is very similar, very typical of a polymer addition in the mix. You get a dark gray salt and pepper appearance, and you can see some air entrainment in the mortar, with dominantly made using a coarser fraction of sand and the dominantly finer fraction of crushed silica sand in a silica flour and polymer based matrix. There are some micro cracks which are seen with blue epoxy, shrinkage micro cracks in the mortar. Air verts are all seen with the blue epoxy. So there are multiple sections of this mortar. Pieces are present in the thin section. Then this is the interface again between the jointing mortar and the brick. Then back to the microstructure of brick showing parallel elongated voids, shrinkage microcracks, whatever way you may want to say it. And these codes of fractions of these rock particles show previously fired clay with original silica quartz grains of the clay, sealed sides quartz grain, and fused matrix from firing. These are the rock particles of previously fired brick, fine sealed size quartz, and semi-fused to fused matrix of clay. This brick is made using rock particles as the major tempered material, as the quartz fraction, and then the finer fraction is quartz and feldspar sand. Everything is in a reddish brown aluminosilicate matrix of fused clay. So this is the third thin section I wanted to show with this Basler Microscopy Software, that how clearly you can see different features, and again you can save them as you see by snapshot. You can play with the brightness contrast if you need to increase or decrease, but usually I set it one value and I don't play with those values from sample to sample. Sharpness you can change if it is not sharp, but usually you get pretty sharp image to begin with, so you don't have to really play with the sharpness or saturation or hue. These values are adjusted based on what I see through the eyepiece, so to make sure that what I am capturing is as close as possible to what I see through the eyepiece. So this is the third sample, a refractory mortar and brick from a chimney environment. Thank you. I'm going to show a thin section of concrete in Basler's Pylon viewer software, which is a software used for industrial camera. Before I showed the microscopy camera and the Basler microscopy software, this time I'm using their industrial camera attached, which is an ACE ACA 2500 60UC, where 2500 stands for 5 megapixel resolution, 60 stands for 60 frames per second frame rate, and UC stands for USB 3 camera, color camera. So that's the one I'm using, attached to a Nikon Eclipse E600 epifluorescent microscope, where I'll be showing a thin section in plain polarized light, crossed polarized light, and fluorescent light mode. So this is the Pylon viewer software, which you can freely download from the Basler website. Once you open the software, it will see all the industrial cameras connected to your computer. I'm using the Macintosh platform, the Apple Mac, using a MacBook Pro. You can use it in the Mac as well as in the Windows software. The previous one, the microscopy software, is only Windows based. The microscopy camera and the microscopy software, they're just Windows based platform, but the industrial camera and the Pylon viewer software can run both in Windows as well as Mac platform. So once you open the Pylon viewer, you go to the device, it shows you all the USB cameras, or if you have any camera which is connected by the Ethernet. Basler also has Ethernet port connected cameras used for industrial applications, but for most of the concrete petrography work we use the USB 3 camera because of high frame rate and high speed. And here you can see there are two cameras right now attached to to the computer, so it's showing those two cameras, but this is the one which I am going to use for the Nikon Eclipse E600 epifluorescent microscope. So if you double click that, then you have to click the continuous shot mode. Once you click the continuous shot, here you see a thin section in fluorescent dye mixed epoxy impregnated thin section, where the fluorescent dye is used to highlight the cracks, the micro cracks in the concrete. This is an old concrete from a breached deck which has been cracked, and the concrete has been impregnated with this dye to show the cracks. And here I'm going to show you, this is the plain polarized light mode. Once you get the image, first you play with the setting. You can save whatever setting you use as a favorite. These are my favorite setting. You go there in the Basler camera mode, then you go to acquisition control, and in the acquisition control it shows the shutter, global shutter mode. Exposure auto, I keep it off because I manually control the exposure, and exposure time. So from this list of parameters, I selected this list of favorites that I'll be using most of the time. The trigger mode has to stay off all the time. The trigger mode off, exposure auto off. I just drag this there when I select those parameters that I need under the favorite section. So these are the acquisition control. Then you have auto function control, auto target, auto function, auto gain, image quality control, what's your light source that you are using, and if you want auto white balance, color adjustment. All these parameters usually I don't play with that much, except the white balance, because you got to make sure you get the exact white balance. And then I bring the other parameters. These are the parameters that I bring from all this list of parameters. The auto function, the minimize gain, I keep the gain minimized for exposure for still photos, but when I do scanning, then I do minimize exposure time for whole slide scan photos. But for still photos we keep minimize gain. And this is the brightness, auto brightness, I keep it at a first fixed value. Trigger mode off, exposure auto off, and exposure time, this controls the actual brightness of the sample. Exposure time, then the brightness, white balance on, balance white, white balance, I can do it once, or I can do it off, or I can do it continuous, and you do that with a blank glass slide. And then light source, acquisition frame rate, gain I usually keep at the lowest, 0.0. Gamma I keep at a reasonable value to get a nice contrast. Then exposure time, which controls the exposure of the image that you are getting. So these are the parameters that I play most of the time, so I listed them under favorite. So I don't even open the other ones, just go there. So when I have to play with the exposure, I just change the bar, move the bar left and right. I can put a crosshair, I can put a grid, I can put a crosshair, I can put just the crosshair, and this is very helpful when we use this camera for air void analysis. This is the camera we use with modified point count method. We get a nice crosshair in this Basler Pylon viewer software. We can maximize the stage and press the escape button to come back. 100%, maximize, escape to come back. You can zoom in and zoom out, and when you zoom in you play with the focus. I have a joystick This is a motorized XY stage that is connected to this microscope. It's a prior motorized XY stage with OptiScan controller and a prior joystick, and the joystick has XY movement at the same time Z axis for focus. So I can rotate the Z axis focus knob in the joystick to get the sharp focus. So this is the plane polarized view, and to capture an image we basically press Command S in the keyboard, file save image, Command S, and we can instantly capture an image. The only problem with Pylon viewer, since this is not a microscopy software like Basler Microscopy Software that I showed before, since this is used for industrial applications, not microscopy application, you cannot create a scale bar or put a scale bar in the image or calibrate your objective. So what you do is you save an image with a stage micrometer at different objective, so you know the length of a known scale in a stage micrometer for a particular objective. Then you open image J and you calibrate your image based on the captured image of a stage micrometer at a particular objective. So that's how the images are, scale bars are put on each captured image. We remember the objective I'm using. Usually I stay at 10x objective. There is a 2x also in this particular microscope, but the 2s and then 10x, I usually use the 10x mode for fluorescent light observation. So this is the plane polarized view. Then to get a cross polarized, I have a slide in and out analyzer that gives the cross polarized view. And to get the light little brighter at the cross polarized, I increase the exposure time just a tad bit. There is a pathetic feldspar. You have the exolution lamellae of albite and orthoclase in a granite sample. These are the exolution lamellae of sodium and potassium feldspar. Carbonated paste. The microcracks are not so clearly seen as in the plane polarized mode. Now from plane polar, so this is an epifluorescent microscope where I move the stage with the joystick from one direction to other, and the same microscope is used to scan a portion of the thin section with the whole slide scanner, whole slide scanning software. Once we get a portion of the image we want to capture, we play with the focus, make sure the focus is sharp, make sure this is a proper setting to see the features of interest clearly. Then we capture the image with Control S. Let's capture the first image as test 1 in the desktop. Then I take a cross polar image at the same position. Only thing I change is the exposure time. Command S, test 2. Then to go to the fluorescent mode, what we do is we shut down the transmitted light, which was open for plane and cross polarized light. We shut down the transmitted light, we close the transmitted light, we open the fluorescent attachment, the shutter for the epifluorescent light, and I move the filter to open the fluorescent filter. Once we open the fluorescent filter, we turn off the light from the transmitted base, and we turn on the shutter to let the light come from the reflected attachment. Then we get the same feature in the fluorescent light mode. We play with the exposure a little bit, exposure time, to get the feature, the crack. To highlight the cracks in the UV light. And there is no fluorescent light mode in the industrial application like you have in the microscopy camera, microscopy software. You have the fluorescent light mode, but in the industrial camera you can still highlight the cracks in the fluorescent light. And to go back to the plane and cross polarized to the transmitted light mode from the reflected light, you close the shutter for the reflected light, you move your filter cube, and then you open the transmitted light. That's how you go back to your transmitted light view. Again, to go back to the reflected fluorescent light, you close the light source at the bottom, you open the light source at the epifluorescent attachment, and you bring the filter. You just slide the filter cube turret to get the right filter, where the filter cube has a excitation filter of 465 to 495 nanometer, a diachroic meter of 505 nanometer, and the barrier filter of 515 to 555 nanometer. That's the filter cube used with the mercury light, 100-watt mercury light, to get this fluorescence image where the cracks are highlighted, everything else is dark by the typical fluorescent microscopy. I can maximize the image to see, and I can move the stage to show the cracks, the voids, all the open areas that are filled with fluorescent epoxy are highlighted beautifully in the fluorescent light mode. And fluorescent light microscopy is a very popular contrast enhancement technique used in concrete petrography by impregnating the thin sections with a fluorescent dye mixed epoxy. A low viscosity epoxy is used, about 100 to 110, 150 centipoise viscosity, and you mix with that low viscosity epoxy the fluorescent dye, and then use that dye to impregnate, use that dye mixed epoxy to impregnate the sample before preparation of thin section. And at any position, if you want to capture an image, Command S, then that will capture an image. And once you capture the images like that, you can open them. Plane polarized, cross polarized, both in transmitted mode and the reflected epifluorescent image. So that's how the Basler camera, industrial camera, and the Pylon viewer softwares are used. And the Pylon viewer is a very popular software. I'm going back to the transmitted light mode. It's a very popular software used in industrial application, and this is very helpful for both Mac and Windows based platform. And in this particular microscope I have a rotating polarizer attached at the base and a slide in and out analyzer. Since this is not a polarized light microscope, this is an epifluorescent microscope, so the polarizer and analyzer are added separately. And this is a Nikon polarizer with rotating polarizer, and a Nikon analyzer slider are added to get the cross polarized light view. So when we do the fluorescent dye mixed epoxy, we get an area where the cracks are visible. We take an image in the plane polar, then cross polar, then we close the transmitted light base by putting a barrier on the top, then open the shutter for the reflected light attachment, bring the filter cube and capture an image in the fluorescent light mode. That's how a same particular feature can be seen in plane polarized, cross polarized and fluorescent light mode. I just change from transmitted to reflected to the fluorescent mode. You have to increase the exposure time a little bit to bring the fluorescent image again. So that's how simultaneously transmitted light and reflected lights are used to observe concrete that has been cracked, and cracks are highlighted by the fluorescent epoxy. Thank you.